Okay, now we have three members. Okay, so we have one member acting in this direction. Okay, so this is one of our members. Hold on, I do apologize. So this is our fastener first. Okay, so this is okay. So what you see down here, so we have member number 1, you have member number 2, and you have member number 3. Right? Then over here, this is our fastener. And this is member number 3 cross section. And you have member number 1 and member number 2. Okay, and we are going to assume that failure, right, will occur over here now. It will occur in the top part and over here. That's where failure will occur. Whereas this one, there's only one line or one area. It says failure will occur. So when this is the case, the shear stress is equal to P divided by 2A. Why 2A? Because failure can occur either in this area or this area. And we're going to assume that it's going to fail at the both rate lines. Okay, in reality, no, but that is our assumption when we do our calculation. Okay, so why 2? Because we have failure at the top rate line and the bottom rate line, and A is again cross-sectional area. Of the fastener. Okay, so now you can see yeah, or now you know the difference between single shear and double shear configuration. Okay, now why do I elaborate on that? If we look at our cross section now, okay, right? So if we focus on our cross section, which is this diagram over here, right? So if we were to look at the cross section over here, what we have over here is the fastener. And if you look at the members, you have member number 1, member number 2, and then you have member number 3. Right? So you realize that if you have 3 members and 1 fastener, this case you have a what? You have a double shear configuration. Okay, not a single shear anymore. We have a what? We have a double shear configuration. So how will this affect our shear flow? Okay, so now the question is, how will the double shear affect our shear flow now? Okay, so we know that the formula that we're going, so the first thing of all, okay, we are going to calculate mode 1 failure. Okay, So there are three modes. Okay, so one, so I'm going to call this mode 1. Okay, mode 1 is resistance of the 600 pounds under single shear with a spacing of 6 inch. Then we're going to calculate mode 2, which is due to the maximum allowable stress of the wood. And then we're going to calculate mode 3. Okay, why I do it this way? Because now we are learning on resistance of the fastener. That's a more critical one. Mode 2, you know how to calculate already. Mode 3, you also know how to calculate. But let's do mode 1 first. Okay, right. So mode 1 that we are going to do. No one have question. So mode 1 is failure of the fastener. Okay. So we know that the formula that we're going to apply is Q is equal to resistance of the fastener divided by spacing. Okay. So we are given the resistance force, right? We are given the resistance force is 600 pounds, single shear. Right? And then we are given the spacing, which is equal to 6 inches. Okay. So now let's recap what did we learn. Okay. So shear stress is equal to P divided by A for single shear. Shear stress is P divided by 2A. Okay. So if we arrange the equation, P is equal to shear stress multiplied by A. Right? Over here, when it's double shear, P is equal to 2 shear stress divided by multiplied by A. Not divided. So twice. Okay. So we realize that the resistance force is twice for double shear. The resistance force is single for single shear. So therefore, for this case, this will be equal to 600 multiplied by 2. Right? And this is because of double shear. And then divide by the spacing of 6 inches. Okay. So this is equal to 200 pound per inch. Right? Makes sense, right? Because over here, if it's single shear, is P over 2A. Double shear is P equal to tau multiplied by A, right? So we realize that the resistance force, the P over here, is twice. Okay, so that's what you have to know about double shear configuration. Okay, so that is our resistance of the fastener, and we know the shear flow is equal to VQ over I. Okay, so what we need to identify now is the V. Okay, so what we don't know is we don't know what's a V, we don't know what's a Q, we don't know what's the I. Okay, right. So now we are going to look at how to determine the V value. Okay, determine V. Okay, so we are going to construct a free body diagram. Okay, so our structure. So this is our X, Y, and this is our rotation about Z. And we know that we have a force down here. I'm going to call this our point A. Okay, this is our point B. So this is our AY, and this is our BY, and then we have a force applied down here, which is equal to P. Okay, so we know that the distance, we are aware that the distance from here to here, oops, is 4 inches. Sorry, 4 feet. This is given in the question, okay? So in terms of inches, it is 4 multiplied 12. So it's equal to 48 inches. Okay, so 4 multiplied 12, this is 48 inches. Okay, so we are going to apply static analysis. And knowing that the structure and or the geometry and applied force is symmetry about the y-axis. Okay, so therefore ax is equal, sorry, ay is equal to by. So then we can do summation about forces in the y direction is equal to 0. So what we have is ay plus by by minus p is equal to 0. So because ay is equal to by, 2ay is equal to p, right? So ay is equal to p over 2, which is also equal to our by. Okay, but if you don't know, or if you are not sure about this statement over here, don't worry. Okay, you can still do the same thing. Or sorry, you can still carry out static analysis, but all you need to do now is to consider the moment. Okay, so what we have is summation about moment about the z-axis at point A is equal to 0. So you have, we're taking moment at point A, so it's equal to minus 48 p, right? Then plus by 96 by, and the whole thing is equal to 0. So by is also equal to p over 2. Okay, then you do summation about forces in the y direction again. Your answer is going to be the same. Okay, right. So now the next thing we're going to do is we're going to construct our shear force diagram. Okay. So this is really straightforward one. So what we have is we're going to have our axis. Okay. So this is our x. This is our shear force. So what we have, so this is 0. This is at 48 inch. This is at 96 inches. Okay. So this is at our point A, and this is our point B. So what we have is we have our forces doing this. Okay, so we have P over 2, and then at 48 you have P coming down, and then you have the horizontal, and then you have our reaction at point B, which is equal to P over 2. Right, so we know that this is P over 2, the maximum.